This is Lab 4, Oscillations by Hudson Grover. The purpose of this lab is to show the motion of oscillating objects. So the spring will be going like up and down and right and left, and it'll be following like the same position over a certain period of time. And the preview is observed does not match perfectly with the model, and you'll see. And then we'll be using the velocity update formula, the position update formula, and newly the energy principle, which will be using kinetic energy, which is 1/2 mass times velocity squared. And then for our potential energy, spring potential and gravity potential. So during our experiment, our system will be Earth, the spring, and the mass, and there will be no surroundings. So this means we can work with potential energy with all those things. And our initial conditions will be this position, 0 velocity, delta at a 0.095 seconds, gravity, this is the coefficient of the spring force, and this is L naught. So for our code, we have our length will be the ball position minus the spring position, so where the spring is and where the ball is will be our length, like the distance between them two. L hat equals L divided by the magnitude of this L, and S is just the magnitude of that L minus L naught. So then to calculate kinetic, we'll be looking at that equation from the first slide and all the potentials, and this is just the coded version of that. And E, importantly, is going to be set to 0 because this is a contained system where there's no surroundings, so the total energy should be 0. And so then in our while statement, which goes to 9.497 because that's how long the actual experiment lasted, we'll be redefining these things because it's important for this while statement to have these predefined as our initials. And then we'll calculate the force of gravity, the force of the spring, and then we'll add these together to get the F net. And then we'll update the velocity, and we'll update the position. And then, once again, all these little initials up here and over here, we'll have to redo every single time because the position of the weight changes. So then we recalculate kinetic, and then we find the change in kinetic by doing the new kinetic minus the initial kinetic. And we'll do this with each of them, and energy stays at 0. And then we will plot all this, and we will get to see what it looks like on a graph. And on the graph, what we'll see is the energy remains at 0, as you can see, and the potential energy oscillates, and all the potential energies and kinetic oscillate, and they stay consistent with each other. So then, for our position versus time, you see in red is the experiment and blue is our model. They actually look very similar. It's just that the model reaches a little farther for the x, and it stays at the same values during y. And the reason this is different is because in the actual experiment there are other forces, so the energy is dissipated as it goes on, so there's not as much energy, which we can see in our possible sources of error, stuff like the friction in the spring and drag from the air. Okay, so what does this mean? For the model system, is the energy principle satisfied? Yes, in the model is, because energy is always equal to 0, and in real life, in the experiment, it would not because of the other forces as we've discussed. And then using the data we obtained in the tracker, I calculated the oscillation periods. Actually, that equaled the same for me for x and y of 1.519 seconds, meaning the starting position, it moved, and then it came back to that same position in 1.519 seconds. And thank you.